Hi guys, welcome to this video where we're going to take a look at another interesting problem from mathematics, where we take a more thorough look at the problem solving process and what that might look like when it comes to trying to find a solution to a non-routine problem in mathematics. And this is going to be particularly important for those of you who are doing A-level maths, wanting to do maths at university, and who will need to do the mathematics admissions test as part of your university application process. The problem that I've chosen for this particular video is from an MAT, from the 2019 MAT past paper, and it's question 2 from that paper. Now, I've chosen this not because the problem is particularly difficult, but more because I found it quite tricky in some parts of this to clearly articulate and justify the ideas that I had. Okay, and this is particularly important when it comes to writing out a solution to a problem in mathematics, or I imagine in other fields of work as well. You need to learn to write clearly. It's very often the case that sometimes I'll set a problem for one of my tutees, for example, as a homework problem, and they might come to me the next time I see them with their solution, or alleged solution, should I say, on a bit of paper. They'll hand it to me, and I'll take a look at what they've written, and I've got no choice really but to hand it back to them and say, I've no idea what's going on here. I don't know what you've written, because it really just looks like a page of random scrolls, Egyptian hieroglyphics or something like that on the page. There's implication symbols all over the place, and there's equals signs, but the things on each side of the equal sign are not even equal, and things like this, and it makes it impossible to really follow what's going on. So understand that as the author of your solution to this problem, it is your responsibility, and I really emphasize it is your responsibility, to make sure that you articulate your idea as best you can. It doesn't have to be perfect, but just like when you write an essay, for example, or even when you write an email to somebody, you're wanting to communicate some information to that person. You need to communicate some kind of idea. Maybe you want to meet somewhere or whatever, I don't know. Well, this has to be communicated in a clear way. There might be many ways in which you can do that, but it still has to be communicated in a clear way. And it's no different with mathematics. When you use these symbols and things like that, these symbols that you write, they mean something. They are effectively a language. And just like when you use everyday language, you have to use it in a particular way to be understood. You have to use this written language also when you write out your solutions in a particular way, or in particular ways, so that you're going to be clearly enough understood. And if you don't write clearly enough, then your solution may not be understood. And don't expect that just because you've written something, you've written a few symbols, that somebody will understand it. That it may be the case that you hand your solution to somebody and they can kind of decipher what you've done, but they shouldn't have to do that. It is your responsibility to make sure that you write out your solution clearly. Okay, so without further ado then, let's get on with the problem. If it looks like I keep looking beneath the camera, that's because my computer's just beneath the camera, and that's where the problem is. Okay, so question 2 from MAT 2019. I'll leave a link in the description to this video so you can download that and you can see the question for yourself. So we start out with, for k a positive integer, we define the polynomial p sub k of x as the following. So p sub k of x is equal to, and it's 1 plus x times 1 plus x squared, all the way up to 1 plus x to the power of k, which in turn is equal to a0 plus a1 times x plus all the way up to a sub n, that's uppercase n, x to the power of uppercase n. Okay, so evidently this is what we would get if we were to expand all of this out. Okay, so where a0, a1 up to a sub n, by the way, they're the coefficients of the polynomial. Okay, right, so the first problem that we've got is part one, is write down the degree n of the polynomial p sub kx in terms of k. So there's a few things that you need to make sure that you understand here, which I'm sure you probably do, but just to clarify, first of all, you need to know what's a polynomial. Okay, well, a polynomial is an expression of the form, and I use b instead of a, so it's going to be b sub r x to the power of r for r equals 0 to n. Okay, so it's, if I were to write this out, it would look like b0 x to the power of 0 plus b1 x to the power of 1 plus up to bn x to the power of n. Okay, so in other words, we get non-negative integer powers of x, 0, 1, 2, 3, up to n. Okay, so the coefficients b0, b1, up to bn, some of them will be non-zero, and some of them will potentially be 0. Okay, if we assume that bn is not equal to 0, then that means that the greatest power of x that we see here is n, and that's the degree of the polynomial. So the degree of this polynomial, so the sum of br x to the power of r from r equals 0 to n, is equal to n. Okay, now if it might be the case in some cases that b sub n is also equal to 0, in which case, okay, the degree is going to be less than n. But just to keep things simple, we may as well assume that this is the coefficient with the greatest subscripts, a non-zero coefficient with greatest subscripts, if that makes any sense. Okay, so this is what we mean by a polynomial, and this is what we mean by the degree of a polynomial. Okay, now there are some issues when it comes to the zero polynomial. How do we define the degree of a zero polynomial, for example? That doesn't really concern us at this stage, but that is kind of an issue. Sometimes it's defined as minus infinity, but we're not going to get into that in this video. We're going to assume that we're not dealing with zero polynomials, or the zero polynomial, should I say. So why am I making a big fuss about this? Because, first of all, if you don't know what is meant by the degree of a polynomial, you can't really set about solving this problem until you know that. This is always the case. When you're trying to solve a problem, if you don't even understand the problem that you're trying to solve, good luck trying to solve it. So, if we think then, provided that a sub n here is going to be non-zero, which it's going to be, how is this going to come about? How is this greatest power of x going to come about? Well, it's going to come about from multiplying x with this x squared, with the x cubed that's going to be next to it, and then all the way up to x to the power of k. Now, using laws of indices, this is going to be x to the power of 1 plus 2 plus plus k. So therefore, n must be the sum of the first k positive integers, which is going to be k times k plus 1 over 2. Well-known formula, okay? And that's going to be quite useful to us at some point later on. So we might want to make a note of that, okay? Time for a quick sip of coffee. Okay, so that's the first part done. Nice and easy. Second part, by setting x equal to 1 or otherwise, explain why A max is greater than or equal to 2 to the power of k over n plus 1, where A max is the greatest value coefficient. So because we've got a finite number of coefficients, there must be a greatest one amongst them. And we don't know which one it is necessarily, but whichever one it is, we're just gonna denote it A max. It doesn't really make any difference which one it is, to be honest with you. Okay, so by the way, one thing that if you are looking to go on to do mathematics at university, one thing that you will get much more comfortable with is dealing with inequalities and finding bounds and things like this, which is not something that you tend to do so much at A-level maths, but you will develop great facility at manipulating inequalities. That's not to say that every inequality that you come across will be straightforward to derive or anything like that, but you will start to think much more in terms of inequalities, particularly when it comes to doing things like real and complex analysis. You'll be thinking much more in terms of inequalities rather than equalities. Okay, so how do we get this? So maybe the first thing to notice is that, or one of the things to notice is that in this expression here, there's going to be n plus 1 coefficients. Okay, this is something that's going to be important to us, because that gives us, noticing things like this can kind of give us a bit of a clue as to where we might need to, which direction we might need to go in. Okay, so n plus 1 coefficients, we see the n plus 1 here, could have something to do with each other. Also, we're given a hint. Where is it? By setting x equals 1 or otherwise. Now, okay, the or otherwise does leave the doors wide open to other possibilities, other possible solutions, ways of going about this problem. But my advice is make life easy for yourself and use the hint that you're given in the exam. Now, at this stage, when you're not in the exam, okay, maybe explore a little bit, because you've got time to do that, and it's a good thing to do. In your exam, that's not a good time to be kind of exploring different ideas and things like that. If you're given a hint, use it, okay? But before you get into the exam, if you're doing past papers and things like that, you're preparing for the exam, by all means, have a little wander around, see what other possible solutions you can find. Okay, so where do we need to go with this, or where can we go with this? Well, we can calculate pk of 1, as the hint suggests, in which case we're going to get 2 times 2 times 2 k times, right? So we're going to get 2 times 2 times 2 times 2, and there's going to be k of those. And this is equal to, well, if we just substitute 1 in place of x here, we're just going to get the sum of the coefficients, a0 plus a1 plus all the way up to an. So therefore we get that this, which is 2 to the power of k, is going to be less than or equal to n plus 1 times the maximum times a max. Okay, because this is going to be less than or equal to a max plus a max plus a max n plus 1 times. Okay, so I'm replacing each of these ai, a0, a1, an with a max. Okay, and these are all less than or equal to a max. So I'm replacing n plus 1 coefficients, or n plus 1 numbers here, with this number just n plus 1 times. Okay, n plus 1. And the inequality follows. Okay, divide each side by n plus 1, you get a max is greater than or equal to 2 to the power of k over n plus 1. And again, that's something that we're going to need to use later in the video. I think my writing's got a bit lopsided, hasn't it? Okay, so on to the next part of the problem. Oh, by the way, guys, just before we move on, this is a relatively new YouTube channel. At the time of making this video, I've only got a few subscribers. I'd be really grateful if you would show your support for this channel by hitting the subscribe button and hitting the like button, and possibly leaving a nice comment in the comments section. That would be great. Cheers, guys. So, part 3. Let's get rid of some of this. We will need some of these results, but I'll write them on the board. I'll write them up here. So n equals k times k plus 1 over 2, and a max is greater than or equal to 2 to the power of k over n plus 1. We'll keep those in mind. So fix I greater than or equal to 0. Fixed. Explain why the value of a sub I eventually becomes constant as k increases. So this was the first point really in this problem where I had an idea, and it kind of seemed obvious to me why this was going to be the case. But then I had to think, how am I going to communicate that idea to somebody? How am I going to get this across in a nice, clear way? And I emphasize it really doesn't need to be perfect. What you write doesn't have to be perfect, but it has to be clear enough for somebody to actually understand what you're getting at, and for somebody to be convinced with what you've written. Okay? So what I eventually figured out was, let's consider pkx, and this is going to be equal to a0 plus a1x plus a sub I x to the power of I plus up to a n x to the power of n. So this is a common thing to do, by the way. I'm kind of slipping this in here because I want to emphasize its presence. Okay, this coefficient, I really want to emphasize that it's there. And that I'm going to be doing something with it. Okay, so then p sub k plus 1 of x is going to be equal to a0 plus a1x plus ai x to the power of I plus an x to the power of n times 1 plus x to the power of k plus 1. Okay, and then to make this work, I'm going to assume that k plus 1 is greater than I. Okay, k plus 1 is greater than I. This is what's really going to make this work, and it's little things like this that when you get your basic idea, you don't necessarily have these details in, and it's once you start trying to articulate your idea that you realize, okay, yeah, I need to include this. So if I included this right at the beginning, people would be thinking, what the hell's going on here? Why am I including that? It's this, and it might be thought that when I came up with my idea that this was just something that popped into my head as well at the same time. No, this was something that came up later. Once I started doing this, I realized I need an extra condition in there, and you'll see why in a second. Because when I expand this out, what do I get? I get a0 plus a1x plus ai x to the power of I plus an x to the power of n plus all of this multiplied by x to the power of k plus 1. a0 plus a1x plus ai x to the power of I plus an x to the power of n multiplied by x to the power of k plus 1. You might be thinking, this is a lot to write out. But sometimes that's the way that it is to clarify your idea. All of this might have been might have come to mind in a flash, and you understood the idea in a split second. But to really articulate that idea, yeah, sometimes it takes a few lines to do it. My advice is just get on with it. Just get on with writing out your solution. The sooner you start, the sooner you can finish. So why is this important? Well, if k plus 1 is greater than I, then none of these, if I expand all of this out here, none of these, none of the powers of x in here are going to be equal to I. They're all going to be greater than I. So all powers of x are greater than I. Okay, so in other words, none of these coefficients, I'm not going to need to combine any of these terms with this term here. Okay, so we've got the aix, a sub I, x to the power of I. None of these are going to need to be kind of combined with this term. Whereas once we get to in here, x to the power of k plus 1, then I'll get something like the a sub k plus 1 plus a naught is going to be the coefficient of x to the power of k plus 1 in pk plus 1. Similarly, a sub k plus 2 plus a to the power of 1 is going to be the coefficient of x k plus 2 in pk plus 1. Okay, but what we can see is that the coefficient of x to the power of I in pk plus 1 of x is equal to the coefficient of x to the power of I in p sub k of x. And we can continue this. So the coefficient of x to the power of I in pk plus 2 of x is going to be equal to the coefficient of x to the power of I in p sub k plus 1 of x, and hence in pk of x, and so on and so forth. So in other words, p k plus j of x, the coefficient of x to the power of I in pk plus j of x is going to be equal to the coefficient of x to the power of I in p sub k of x for j, an integer greater than or equal to 1. Okay, so I mean, you could ask the question at this stage, do I have to write all of this out? Do I have to write this out, my idea out in this way? And the answer to that is no. You write your idea out how you think it can be best communicated. But understand as well that your examiner won't be looking for perfection. With the MAT, your examiner's really going to be looking for potential. Okay, as long as you're getting your idea across in a clear enough way and you're showing that you've got good ideas, that's what your examiner's going to be looking at. Have you got the potential to go on to do higher level mathematics, undergraduate mathematics, potentially postgraduate mathematics, PhD or whatever, and be successful? And your examiners know what they're looking for, by the way. They know what sort of mindset and what kind of attitude you need to have, really, to be successful. And this is part of the deal, really, that you can get your ideas across, that you can show that you've got good ideas, and that you can at least start to communicate them, even if they're imperfect. They don't have to be perfect. Okay, so on to the next part of this problem. So on the basis, a student correctly calculates for k equals c that p sub c of x is equal to, and it gives an expression which I'm not going to write on the board because actually it doesn't really, the exact expression that the student obtains for p sub 6 of x is really not important. All the expression illustrates, it gives some motivation as to why the student goes on to make a couple of conjectures. Okay, so we're informed that the student makes two conjectures, one which is right, one which is wrong, but both of the conjectures are obviously motivated by this expression that's been obtained for p sub 6x. Okay, and this is a common thing to do in mathematics, that based on a finite number of cases, so you work with a finite number of cases and you kind of see a pattern emerging. At that point, you might feel justified in making a conjecture. So you're not saying that because you think you've seen this pattern, that it definitely is there and it must continue. You're saying, well, I think I've seen this pattern, therefore I'm going to suggest it as a conjecture, something that we might go on to try to prove in more detail. Okay, it might turn out that your conjecture is wrong, and that's what we'll see in one of the parts of this problem. But this is a perfectly normal thing in mathematics to do, and this is kind of similar, I guess, to inductive reasoning, I guess, in the inductive sciences. It's just that in mathematics, even though you suggest a particular conjecture that you've kind of generalized from a finite number of cases, it still then has to be proved in a satisfactory way, in an adequate way, to show that it holds in all cases, usually an infinite number of cases. So let's have a look then. So student correctly calculates p sub 6x equals such and such. On the basis of this calculation, the student guesses that a sub I is equal to a sub n minus I, for 0 is less than or equal to I is less than or equal to n. Okay, so the student has made a conjecture, made an observation, and when you download the past paper, the 2019 past paper, you'll see why this conjecture would seem reasonable. Because there is a symmetry with the coefficients, an apparent symmetry. What we need to figure out is whether that symmetry always holds, though. So the conjecture is that a sub I is equal to a sub n minus I for 0 less than or equal to I less than or equal to n. So this has a very kind of binomial coefficient sort of feel to it. It's got nothing to do with binomial coefficients, but when I saw this, that was what I immediately started to think about, binomial coefficients. Because with binomial coefficients, of course, you've got the symmetry with them. Okay, so that was just one of the thoughts that went through my mind. We're given a hint here again. By substituting x to the power of minus 1 for x, in other words, 1 over x, in place of x, I think, or otherwise, again, take the hint. Show that the student's guess is correct for all positive integers k. Okay, so we're given a big hint. Let's go with it. So, p sub k of 1 over x is going to be 1 plus 1 over x times 1 plus 1 over x squared, 1 plus 1 over x to the power of k, and this must be equal to a naught plus a1 over x plus up to a n over x to the power of n. Okay, so what do we do now then? Well, we can multiply through by x to the power of n, both sides. So we get x to the power of n times 1 plus 1 over x times 1 plus 1 over x squared, 1 plus 1 over x to the power of k, is equal to a naught x to the power of n plus a1 x to the power of n minus 1 all the way down to a n. Now this here we can think of as x times 1 plus 1 over x times x squared times 1 plus 1 over x squared times all the way up to x to the power of k 1 plus 1 over x to the power of k, which is equal to x plus 1, x squared plus 1, x to the power of k plus 1, which is equal to p sub k of x. In other words, p sub k of 1 over x multiplied by x to the power of n is equal to p sub k of x. Okay? And therefore, remember, p sub k of x is equal to this, but we've just shown it's also equal to this. So that means that the coefficient of x to the power of n here must be the same as the coefficient of x to the power of n here. In other words, an is equal to a naught. The coefficient of x to the power of n minus 1 here has to match the coefficient of n minus 1 here, x to the power of n minus 1 here. In other words, a n minus 1 is equal to a1. Similarly, a n minus 2 is going to be equal to a2, and all the way down to a naught is going to be equal to a n. So what we see is that a n minus I is equal to ai for all integers I between and including 0 and uppercase n. Okay, so again, take the hint if you're given a hint. That was a nice, easy little thing. This wasn't particularly difficult. I didn't feel that there was anything really difficult about this particular problem. The next one, however, again was kind of obvious to me in many ways, but trying to find the right way to articulate and to justify what I wanted to say. That was a different issue. Okay, so we can get rid of this. We've done that part. I'll write that up here actually, just in case. AI equals a n minus I, 0 less than or equal to I less than or equal to n. Okay, just in case we need it. Okay, so the final part on this is that, let me just scroll down a little bit. On the basis of the same calculation, in other words, the calculation that the student's done for p sub 6 of x, the student guesses that all whole numbers in the range 1, 2, up to and including a max appear amongst the coefficients a naught up to a sub n for all positive integers k. Use part 2, again, hint, to show that in this case the student's guess is wrong. Justify your this is important. Justify your answer. Okay. So again, the calculation that the student has done for this p sub 6 of x, it's really we're told what that is really to show why the student may have arrived at his conclusion. Or this possible conjecture, okay? But then it still remains, even when you make a conjecture, and this is perfectly fine to do this, even when you've made a conjecture, you are still obliged then to go ahead and actually prove that conjecture true or false, as the case may be. Otherwise, it's unknown. You can't necessarily use that conjecture in the proofs of other things without acknowledging that that thing hasn't yet been proved. Okay, so it mustn't be taken as being true until it's actually being proved true, or false unless it's being proved false. Okay, so I tried a few things for this. I knew which direction I wanted to go in. The fact that you've got a max here is greater than or equal to 2 to the power of k over n plus 1. And as I noted earlier, we've got n plus 1 coefficients. What I wanted to somehow show is that this number, 2 to the power of k over n plus 1, must at some point get so great that, in particular, it's got to be greater than or equal to n plus 2. At some point, this is going to be greater than or equal to n plus 2. And at that point, if a max is equal to n plus 2, it might be greater than n plus 2, but let's say it's equal to n plus 2. Then, because there's only n plus 1 coefficients, then there's no way that you can account for n plus 2 integers in only n plus 1 possible coefficients. Okay, one must be missed out somewhere. One of the integers must be missed out somewhere. So if a max is equal to n plus 2, then there must be at least one number between 1, 2, or one integer between 1, 2 and a max that is not to be found amongst the coefficients, because there's just not enough coefficients there. That was my idea, okay? And it seemed that was definitely the direction that I wanted to go in, but then it was, how do I get to this result? Okay, it's one thing. By the way, even if I was doing the test, the MAT, I would still express this idea. Okay, even if I couldn't find a way to fully justify it, I would still express this. Make sure you express your ideas. Okay, that will count for something. When it comes to problem solving, whether it's in an exam or not, having ideas is the most important thing. Having ideas and being able to try to follow through on them. Okay, much of the time, if it's a good problem, if it's a good challenging problem, then yeah, some of your ideas are not going to work. But having ideas that don't work is better than not having ideas at all. And trying out ideas that don't work is better than not trying out any ideas at all. Okay, so at least if you've got an idea, even if you don't know how to properly follow through with it, in your MAT, just express the idea. Okay, that's what your examiner is going to be looking for. Ideally, yes, you want to get a solution, but if you can't get a solution, at least show that you've got an idea of what you would like to do, even if you don't know how to do it, because that can come further down the line. The examiner, whoever's marking your exam, will recognize, yeah, this person's got some potential. They've got some good ideas. Now we just need to build them up a little bit so that they can follow through on those ideas a little bit more. Okay. So I tried out all sorts of things actually. Let me just refer to my notes. So yeah, I had this idea that if a max is greater than or equal to n plus 2, because you've only got n plus 1 coefficients, then you can't possibly account for all of the numbers. Then I thought, okay, what if a max is actually equal to n plus 1? Well, in that case, if a max is equal to n plus 1, then all of the numbers can be accounted for, but there must be each integer between 1, 2, up to a max inclusive, must be represented once and exactly once amongst these coefficients. In other words, the sum of the coefficients is going to be the sum. So a0 plus a1 plus up to an is going to be equal to 1 plus 2 plus up to n plus 1, which is going to be n plus 1 times n plus 2 over 2, for example. And this must also be equal to, because we know that 2 to the power of k is equal to the sum of the coefficients from what we did earlier, then that means that 2 to the power of k is equal to n plus 1 times n plus 2 over 2. So that means that I could substitute that into here, into this inequality. 2 to the power of k replaced with n plus 1, n plus 2 over 2. So I'd get A max is greater than or equal to n plus 2 over 2, which didn't really have the desired effect. Again, it was an idea that I had, and sometimes you've just got to kind of plow through and see what happens. So the point of these videos, by the way, is not to just give you a model solution to these questions. There's mark schemes that can do that. What I'm wanting to do is to show how my solution has actually developed. The kind of ideas that I've had to go through to, the incorrect ideas, in many cases, that I've had to go through to get to the right idea. Okay? Okay, A max is greater than or equal to n plus 2 over 2, but then I thought, hang on a second, what about the symmetry of the coefficients? Because I know if this is equal to 1, which it's bound to be, then this must also be equal to 1. This coefficient will be equal to the penultimate coefficient, and so on and so forth. So actually, A max couldn't even be as big as n plus 1. It would have to be potentially less than that. Okay, well, what could it be? And this is where you kind of think worst case scenarios. What's the worst case scenario? Well, if you've got, if n is, let's say n is an even number. Okay, so we might think if n is equal to 2, we're going to have A0, A1, A2. By the symmetry, these two numbers are going to be equal, A0 and A2, and this is potentially going to be another number. Okay, so here we've got n is equal to 2. When n is equal to 4, we're going to have A0, A1, A2, A3, A4. So here we're going to have potentially two distinct numbers. Here we're going to have potentially 3 distinct numbers. N equals 6, we're going to have potentially A0, A1, A2, A3, A4, A5, A6. We're going to have potentially 4 distinct numbers. So I was thinking, okay, maybe I could figure something out from this then. So n equals 2, 2n. So n plus 2 over 2. So if n is even, there's potentially n plus 2 over 2 distinct numbers. Okay, n plus 2 over 2 distinct numbers. So then again, we've kind of got the I can find the sum of the coefficients. If there are n plus 2 over 2 distinct numbers, then each number 1, 2, 3 up to A max must be represented once here, and then we're going to get it represented again here, except for this one in the middle. So I was thinking, right, I need to find the sum of the first n plus 2 over 2 integers, and then the sum of these integers over here, and add them together and get a big expression. This wasn't going anywhere. Okay, it might have done somewhere, but it was getting too fussy, and I kind of gave up with it. So I'm not gonna. That was just another idea that I had. I'm not sure that I've clarified it very well, but it's beside the point because it didn't really turn into anything anyway. Again, what I'm trying to show here is that sometimes you've got to go through some, you've got to go into some cul-de-sacs, into some dead ends sometimes, and work your way back out before you actually find the right solution. Okay? So, let's try, I tried something else then. What I recognized was that I was thinking, how can I make this come about? Okay, how can I get 2 to the power of k over n plus 1 to be greater than or equal to n plus 2? And that would require 2 to the power of k to be greater than or equal to n plus 1 times n plus 2. Okay, because if 2 to the power of k is greater than or equal to n plus 1 over n plus 2, then 2 to the power of k over n plus 1, divide each side by n plus 1, cancel, we're just going to be left with the n plus 2 here. And then I thought, hang on a second, we know what n is in terms of k. Okay, n is equal to k times k plus 1 over 2. So what is this going to be? This is going to effectively be a quartic function of k, quartic expression in k. So I'm going to have something like 2 to the power of k, and on the one hand, and on the other hand, I'm going to have something k to the power of 4. I need to show that 2 to the power of k is going to, for sufficiently large k, is going to be greater than k to the power of 4. Okay, so I'm replacing the n plus, because I know that n plus 1 times n plus 2 is just a quartic expression in k. I'm just thinking about the simplest quartic expression. It's not k to the power of 4, but let's just take this just to keep things simple. Now this is intuitively obvious. An exponential, if I think about 2 to the power of x and x to the power of 4, 2 to the power of x will always outgrow x to the power of 4. There will be some value along the way at which 2 to the power of k is going to be greater than k to the power of 4. Now, in the MAT, it might be sufficient for you to just state that. To say, yeah, 2 to the power of k at some point is going to be greater than k to the power of 4, and therefore, at some point, 2 to the power of k is going to be greater than or equal to n plus 1 times n plus 2, for example. Again, just expressing your idea. But I wanted to be a bit more precise about this. So I was thinking, how can we actually prove in a satisfactory way that 2 to the power of k is going to be greater than k to the power of 4? So instead of k to the power of 4, I thought of k to the power of n. Okay? For some fixed value of n, not necessarily 4. Okay, my idea was the following. So 2 to the power of k is going to be greater than n times k for sufficiently large. In fact, I'll use k primed actually. 2 to the power of k primed is going to be greater than n times k primed for sufficiently large k primed. Really, I guess that does require some proof as well, but I'm going to take that as a bit more obvious because this is just a straight line and this is an exponential. It seems a bit more obvious that the exponential is going to outgrow the straight line at some point. So 2 to the power of n, k primed to the power of n is going to be greater than n k primed to the power of n. So that means that 2 to the power of n k primed is going to be greater than n k primed to the power of n. And so if we set k equal to n times k primed, we get 2 to the power of k is greater than k to the power of n for sufficiently large k. Okay? So in particular, we get that 2 to the power of k is going to be greater than k to the power of 4 for sufficiently large k, and therefore maybe tweak the argument a little bit if you want to be really precise about it. It's kind of obvious that 2 to the power of k is going to be greater than or equal to n plus 1 times n plus 2 for sufficiently large values of k. In which case then we get the result. So 2 to the power of k is greater than or equal to n plus 1 times n plus 2. 2 to the power of k over n plus 1 is greater than or equal to n plus 1 times n plus 2 over n plus 1, which equals n plus 2. That means that A max which is greater than or equal to this, must be greater than or equal to n plus 2. And that provides the result that I was looking for. I wanted to show that A max has to be greater than or equal to n plus 2. Okay, and that concludes the solution to this particular problem. So it's taken a little bit longer than I expected to go through this, but again, I've wanted to try to describe some of the thought processes that were involved in my solution to this particular problem. It also didn't help that I did this late at night, so maybe the thought processes were a little bit more wandering than they might have been had I been doing this, trying to find a solution to this problem when I was a bit more alert. But anyway, that brings us to the end of this solution, and it brings us to the end of this video. Thanks for watching, guys.